and good afternoon everyone. I welcome you all to India's largest e-learning platform, Unacademy, and I welcome you all to my session, Antennas CTQ series. We are into part 16, and today in this session we are going to discuss about concepts of antenna arrays. So let us get up to have some questions and concepts on antenna arrays. Any doubts you can ask, dear. Before we start the session, let me introduce myself. I am G Reddy, having 15 plus years of experience in teaching, guiding and mentoring students preparing for competitive exams, including GATE and ESE. I work as motivational speaker pan-India from the past 12 years, expert in field theory and communications. And this is the link where you can join us on Telegram. The advantage of joining us on Telegram is that you get a personal level support from all the faculties of the GATE Conqueror channel. As you know, 4 new educators added to our channel. Now we are a loop of 8 educators who will teach in English. It's a full team. We are geared up to finish all the subjects of EC and electrical for GATE and ESE. So that's our target, to finish GATE and ESE, all the subjects of GATE and ESE. And we are more than well equipped now to finish off all the subjects comprehensively. And don't miss today's 9:30 p.m. session. Just stay tuned to the channel. The session taken up by K.N. Rao sir, Ram sir and Sham sir. Stay tuned to this. Please make a note and don't miss out this session here. One more wonderful session on the cards. Don't miss out on this session. This session is about why students are unable to plan career during college days, and who else or who better than the legendary K.N. Rao sir can do justice to this topic. So try to utilize all his experience. Along with that, we have some extremely talented and experienced faculties in the form of Sham sir and Ram sir. Try to get the most of this session. Don't forget, today 24th of April, 9:30 p.m. will be the session. 9:30 p.m. will be the session here. Stay tuned to this particular session. One second here. Yes. Unacademy offers 2 paid platforms. One is Plus subscription, other is Iconic. In Plus, you got to have the FaceTime of legendary faculties in the form of live classes, weekly test, structured courses, unlimited access, rank improvement batches and crash courses. In Iconic, you have all these facilities. Along with that, you have a personal coach for one-on-one guidance, dedicated doubt clearing educators to clear your doubts, preparatory study material, personalized test analysis, study booster sessions, and customized study planner. Whether you take a Plus subscription or Iconic subscription, I recommend you to go for a no-cost EMI. The total cost will be divided by number of months. You can use our team code KNR10 to get extra 10% off. And this, make a note that this no-cost EMI is available for subscriptions of 6 months and above. With Iconic subscription, you get 1:1 live mentoring, improving your chance of getting a top rank. This is GATE and ESE Iconic subscription, which has facilities like you have a personal coach, 1:1 live mentoring, online study material, priority in Ask It Out, live doubt solving sessions, study booster sessions, priority in Raise a Hand, open hours with educators, community learning, and also all benefits of Plus. Definitely the Iconic subscription will be next level of your preparation. Free physical notes are available for GATE Iconic 1 year and above subscription. These notes are curated under the mentorship of top educators, which has comprehensive syllabus coverage, solved examples to build problem solving skills. This material is available for electrical, EC, mechanical, civil, and computer science. With Unacademy Lite subscription, you get lot of variants of mock test, like you get topic and subject wise test, you get access to structured test series, detailed solutions and performance analysis. You can subscribe now using the code KNR10. You can subscribe using the code KNR10, which is our team code, which gives you additional 10% off. This Unacademy Ultra Combat, which is today dear, don't miss it up. Don't miss this. You get 100% scholarship, and you also stand a chance to win exciting gadgets like the form of MacBook, iPad, iPhone, Samsung Watch, JBL speaker, and Amazon vouchers. And the good thing is, lucky participants stand a chance to win Amazon vouchers of worth ₹5,000. This Unacademy Ultra Combat, as I told you, it contains 30 questions. We have 60 minutes into it. Today at 11 AM it has started. You can attend it at any time dear today, and try to be among the top. This is the best time for you to prepare and gear up your preparation for GATE and ESE exam. This Unacademy Ask a Doubt feature, through which you can ask unlimited number of doubts. It is available on website and app. You can ask 3 doubts at a go. I'm trying to hide the video for 1 second here. You can get the solution in your preferred language, and also it is very easy to ask a doubt. Just click, crop, and submit. You can get in touch with our counselor if you have any confusion about your preparation journey. If you have any queries about your subscriptions, you want to know about latest offers, you can dial all 8 5s. The special class features includes interactive live classes, polls for the learners, a raise hand option. You never miss a class when the notification is on. You can download the lecture note then and there. You can access anytime and anywhere. This Ascend GATE 2024 started April 20 for electrical explained bilingual. Ascend GATE 2024 for ECE explained bilingual. Evolve GATE 2023 for electrical explained bilingual. Evolve GATE 2023 for ECE explained bilingual. And you can see here, of course, the one who need not have any introduction. KM Rao sir is here in this batch. Sham sir is here. Ram Mohan Reddy sir is here. And the very talented Archit Kamath sir is here. Along with that, We have also Ramarao sir. All these faculties are from the GATE Conqueror team. You can see how strong the team is now. And we are ready, as I told you, we are ready and geared up to finish GATE and ESE 2023 syllabi for both ECE and electrical. Sharma sir will be handling networks and measurements. Ramon Reddy sir will be handling analog. Rachit sir will be handling controls. Ramarao sir will be handling devices. Of course, K.N. Rao sir will be handling machines. So these are the primary subjects. Of course, they handle multiple subjects. So now we are having a very strong team for GATE and ESE English team. Those who teach in English instead of bilingual. We are into antennas CTQ series. Wonderful questions up my sleeve today. So just share the class among the maximum, dear. I request everyone to immediately share the class among the maximum so that most of the students will get benefited by this wonderful session. Just kindly share the class among the maximum as soon as possible. Any doubts you can ask, dear. Yes, dear. Any questions you have, you can ask. As you know, we are determined to finish EMFT syllabus comprehensively, which contains 5 modules. Module 1 is elements of EMF theory, which is common for both ECE and electrical. We are covered for both GATE and ESE. This is the complete syllabus for electrical, that is EMF, and 1 module out of 5 for ECE. So I took utmost precaution that all the topics are covered, all the derivations are done, all the previous year questions from GATE and engineering services are covered. So many practice questions have been solved, some tricky shortcuts has been explained. In this module, for this we have created a playlist with 40 videos and 50 hours of content. 50 hours is a very huge content here. For elements of EMF theory, you take on any YouTube channel, you will not find more than 10 hours. Maximum content they can deliver is only 10 hours. Against that, we got 50 hours of content only for module 1. Please don't miss out on this playlist. Just go through this playlist. You will rock this particular module, elements of EMF theory. Module 2. Module 2 is EM wave propagation. EM wave propagation. This is for ECE and 90% of the syllabus is completed for this. and we covered both GATE and ESE exams. I created a playlist for this too. 15 videos and 30 hours of content. 15 videos and 30 hours of content. Again, maximum content for EM wave propagation is around 6 to 8 hours. Again, that only covering 90% of the syllabi. We already got 30 hours here because we covered all the derivations related to engineering services, all the concepts related to GATE, shortcuts related to GATE, and previous year question papers of both GATE and ESE, as well as some numerous number of practice questions. Module 3, and this rest of the 10% I'll complete it today in the evening session. Today evening session I'll complete it, so don't worry. Module 3 is transmission lines. We're starting from tomorrow. And once module 3 is done, we'll start module 4, which is waveguides, which includes rectangular waveguides and circular waveguides. When this is done, then we go for module 5, which is optical fiber communication and antennas, in which for optical fiber communication I'll take a separate series with 10 hours duration at the end, and antennas were already covered in the series called Antennas Mahamarathon series. This is a series especially useful for both GATE and ESE, and more emphasis on ESE. Lots of derivations have been done in this series. Antenna measurements had been explained, resonant, non-resonant antennas had been explained, and like never before, 7 sister antennas had been explained. And this also has 18 videos with 38 hours of content. This is also a unique series, dear. You cannot find a series like this which covers all the antennas. We covered all the antennas. There's one more wonderful series. So almost like 60% of the syllabus is done. We're covering module 1 completely and module 2 90%. In module 5 antennas we had completed, so around 60% of the syllabus is completed already. And today I'll finish this 10% that is left out in module 2, so that module 1, module 2 and module 5 except optical fiber communication will be finished. And from tomorrow we can start transmission lines. So let us start the questions, dear. One second. Yeah. Tell me the answer. Read the question carefully and tell me the answer. Collinear arrays will result in maximum gain and spacing between the elements is dash to dash. 0.2 lambda to 0.4 lambda, 0.3 lambda to 0.5 lambda, 0.2 lambda to 0.6 lambda, 0.4 lambda to 0.6 lambda. It's a design factor, dear. It's a design factor. Kindly answer. Kindly answer, dear. Kindly answer first. Collinear arrays will result in maximum gain when spacing between the elements is dash to dash lambda, this is a design factor. The design factor here, collinear arrays will give you maximum gain when the spacing between the elements is between 0.3 lambda to 0.5 lambda. Very, very important question, because as it is a design factor, you must remember it. There is no other go. You cannot calculate it as of now. So option B is the answer. Question number 1, option B is the answer. Is that clear? Any doubts? Any doubts? A collinear array with two elements. Collinear array with the two elements results in gain of dash dB. Again, one more design factor. A collinear array with two elements results in gain of dash dB, 1.9 dB, 3.2 dB, 4.3 dB and 5.4 dB. A collinear array, two elements results in gain of 1.9 decibel. It's a design factor. Option A is the answer. Therefore, option A is the answer. Collinear arrays with four elements. Collinear arrays with four elements results in gain of dash dB. Let me give you a table here. Collinear arrays. Spacing for maximum gain is 0.3 lambda to 0.5 lambda. Collinear array with the two elements results in a gain of 1.9 dB. Collinear array with three elements results in a gain of 3.2 dB. Collinear array with four elements results in 4.3 dB. Results in 4.3 dB. Okay. Two elements, 1.9. Fine. Any doubt here? You can ask here. Any doubt you can ask. A collinear array with two elements results in 1.9 dB, three elements results in 3.2 dB, four elements results in 4.3 dB. It's a design factor again. Option C is the answer. Option C is the answer. Okay. Fine. Next question. A phasing stub. A phasing stub is used in collinear arrays to make the current. Let me take a collinear array. Let me consider a collinear array. Element 1. element 2, each of length lambda by 2, element 3, and element 4, each of length lambda by 2. Now this is just like current on a parallel wave transmission line. It's like current on a parallel wave transmission line. If you consider current on a parallel wave transmission line, the current will be like this. This is lambda by 2. This is lambda by 2. For every lambda by 2, the current will reverse its phase. The same thing will happen here. This is 1 lambda by 2 plus. Now what is the phasing stub is? It's a conductive element like this, with the total length of lambda by 2. So once the positive here, the negative half cycle will be consumed here. The current is opposite in this direction, they cancel off. Once this negative is completed, the positive cycle will be here. Then again the phasing stub, negative will be consumed here. Again the positive, negative will be consumed here. Again the positive. That means what? The current is now getting in phase. Now you read the question and answer me. A phasing stub is used in collinear arrays to make the current in phase, out of phase, partially in phase, partially out of phase. A phasing stub is used in collinear arrays to make the current in phase. To make the current in phase. Option A is the answer. Any doubts here? Is that clear? In a parasitic array, element to which power is supplied is called. If you take a parasitic array, what is an example of parasitic array? Yagi-Uda antenna, previously used TV receiving antenna, is the best example for parasitic array. It contains a vertical rod. Have you people seen this Yagi-Uda antenna anywhere? Even today, if you go to countryside, in villages, you can see them. There is a stand to hold the antenna. This is a vertical rod. This is a horizontal rod. Horizontal rod. I am using a clamper here to fix it. The element to which the feeding is done. Generally we use a folded dipole here. This is to which the power is fed. This is to which power is fed or power is received. Transmitting antenna power is fed and for receiving power is received. This element to which the power is fed or received is called the driven element. Generally the driven element, Yagi Uda, the folded dipole antenna. This will be approximately of the length of lambda by 2 and with spacing of 0.10 to 0.15 lambda. You will have reflector which is having a length 5% greater than the driven element. The work of reflector is to reflect back the radiation in this direction towards only one direction. Reflector having a height of 5% more than the driven element. These are the directors. Which are having consecutively, which are having height 5% less. Set of directors. This is a Yagi-Uda antenna. It's a high gain antenna. High directive antenna. Now the question is, in a parasitic array, the element to which the power is supplied is called, what is this element here? Driven element. Question number 5. Option B is the answer. Any doubts here? Anyone, any doubts? In a parasitic array, just now I explained about parasitic arrays. Element which is maintained a height 5% less than driven element is director, reflector, corner adder, corner subtractor. You can see here, this is a reflector having 5% height more than the driven element, and these are directors having 5% height less than the driven element. So what is the question? The question is, in a parasitic array, element which is maintained a height 5% less than the driven element is director, Option A is the answer. For visualization, you can also see the Yagi-Uda antennas. You can see the Yagi-Uda antenna. Yeah, here it goes. See here. The Yagi-Uda antenna with folded dipole as a driven element. I'll show you one more. Yeah, this is more clear. See here. Driven element, folded dipole, long one, reflector, shorter ones, director. This is practically installed antenna, you can see here. Clear? Is it clear? The following is an example. Following is an example of parasitic array. Dipole antenna, simple dipole antenna. You have two poles. It's a wide antenna. There is no parasitic elements involved. Monopole, it's just a single pole antenna. Yagi-Uda, as I explained, contains a driven element to which the power is fed, contains set of directors. They're having height 5% less than the driven element, and the reflector having height 5% more than the driven element. The horizontal rod and the vertical rod to hold them. Clearly not dipole. This is dipole here. The practical dipole antenna. You can clearly visualize that there is no parasitic element there. This monopole antenna, very clearly here also there are no parasitic elements. This is Yagi-Uda, which has parasitically excited elements. The following is an example. The following is an example of parasitic array. Yagi-Uda antenna. Option C is the answer. Is it clear? Yagi-Uda antenna exhibit high dash. Yagi-Uda antenna is also called as super gain antenna, super directive antenna, which exhibits high directivity. Today too, if you go to villages, you can see this kind of antennas there. You can see these Yagi-Uda antennas. On the roof there will be a provision to keep this rod. There is a vertical rod. There is a horizontal rod. Today too, you can visualize this kind of antennas. driven element, folded dipole, the directors and the reflector. If you had operated this Yagi-Uda antenna, this is your home and through which the wire is connected to your TV set, the TV receiving antenna. This is the TV station. This directors must be placed in the direction of the TV station. But whenever we have some strong wind, this rod used to rotate. It is to have the position like this. Now, because it is super gain antenna, super direct antenna, it can radiate or receive only in one direction. So here there is no station. So this fellow cannot receive the signal. So you get a lot of dots here. Previously no one used to know about this. But what they know is they need to rotate this until you get a good picture. That's it. The standard rule is the younger in the family will go up and the elder one will see the clarity of the picture. Clear? So now, Yagi-Uda antenna exhibit high FBR. I told you FBR stands for front to back ratio. The ratio of power in front lobe or major lobe to its back lobe. This must be as high as possible. Its practical equivalent is directivity. FBR is equivalent to directivity. Yagi-Uda antenna exhibit high FBR or high directivity, high beam area. You know, directivity is 4 pi by omega A. Omega A is beam area. If it is exhibiting high beam area, directivity will be less. But you know, directivity is more here. So this is not the thing. Antenna temperature is not an integral property of the antenna. It depends on the surrounding. So this option can't be correct. All can't be correct. So FBR is the answer. Because you cannot say that Yagi-Uda antenna exhibit high antenna temperature. Because antenna temperature is not an integral property of the antenna. Antenna temperature is equal to surrounding temperature. Is that clear? Try and answer this. Operating frequency of parasitic arrays suitable for frequencies of. Now you know that parasitic arrays are having advantage. Very clearly we know that parasitic arrays are having advantage. But the question is, can you use it for all the frequencies? There is any limitation for the frequencies. Parasitic arrays, so many advantages, but one limitation is it can be used between frequencies of 100 megahertz and 1 gigahertz. It is 100 megahertz and 1000 megahertz or 1 gigahertz. So operating frequency Yagi-Uda antenna or parasitic array, any parasitic array must be between 100 megahertz and 1000 megahertz or 100 megahertz and 1 gigahertz. Again, one more very important question, because it is a design factor. Question number 9, option A is the answer. The problem of using phasing stubs, because when you use phasing stubs, reversal of current is happening. Losses are increasing. This can be reduced or this can be avoided. Phasing steps can be avoided by dash arrays. In parasitic arrays, there is no connectivity, therefore, there is no need of any phasing stub. So, the problem of using phasing stubs can be avoided if you use a parasitic array. Option C is the answer. Clear? An array of 2-point sources fed with current of equal amplitude and phase results in which pattern? An array of 2-point sources fed with current of equal amplitude and phase results in dash pattern, end fire, broadside, parasitic and all. Broadside array pattern where maximum radiation will be along will be at 90 and 270 perpendicular to the axis of the array. This kind of array results when you apply equal amplitude and same phase. An array of 2-point sources fed with current of equal amplitude and same phase results in a broadside array. The array axis. For a broadside array, we have figure of 8 pattern. The figure of 8 pattern. Radiation perpendicular to the axis of the array or array axis. Maximum radiation at 90 to 270. Minimum at 0 180. Option B is the answer. An array of 2-point sources fed with current of equal amplitude and progressive phase shift results in dash pattern. Progressive phase shift means phase shift is proportional to distance between the elements. How to calculate? If you take a wave, the distance covered by the wave to complete one cycle is called wavelength lambda. Distance is lambda, half of them lambda by 2, 1/4 lambda by 4. This is 3 lambda by 4. Now, if the distance between the elements, this is a 2-element array, distance between the elements, if it is lambda by 4, if the distance between the elements is lambda by 4, then try to calculate the phase shift here. At this point, the phase shift is 0 degrees. Here it is 90, here it is 180, here it is 270, here it is 360. When distance and phase shift are proportional, if this element is given 0 degrees and this fellow is 90, The phase difference is 90 degrees. Distance is lambda by 4. They are proportional to each other. In this case, you call it as progressive phase shift. Now read the question. An array of 2 point sources fed with current of equal amplitude and progressive phase results in dash pattern. Progressive phase results in end fire pattern which will radiate at the end of the array. Option A is the answer. An array of 2 point sources fed with current of equal amplitude fed with current of equal amplitude and phase difference alpha is 0 degrees, spacing lambda by 2 results in dash pattern. The pattern, normalized pattern of an antenna array is given by cos of psi by 2, where psi is beta d cos theta plus alpha. Now you may ask me, sir, from where you got this? Please refer Antennas Mahamarathon series to check out the derivation for this. So ED normal is cos of psi by 2, psi is beta d cos theta plus alpha, substituting beta is 2 pi by lambda, if psi is beta 2 pi by lambda, distance lambda by 2, cos theta plus alpha 0. Psi is pi cos theta. I want psi by 2. I want psi by 2. ET is equal to cos of pi by 2 cos theta. Check out here. What is the radiation pattern that you are getting here? Please check out. First time theta is 0 degrees. Check out cos 0 1. Cos 90 is 0. No radiation. No radiation. Next step. Theta is 90. Next step. Theta is 90. Cos 90 is 0. Cos 0 1. Pi by 2 into 0 0. Cos 0 1 maximum radiation. Cos 180 minus 1. Cos of minus 90. Cos 90 is 0. No radiation. No radiation. Theta is 270. Theta is 270. Cos of 270 0. Pi by 2 into 0 0. Cos 0 1 maximum radiation. Maximum radiation. So it is resulting in figure of 8 pattern. So what's the answer? Option A is the answer. Next question. An array of 2-point sources fed with current of equal amplitude and phase difference of 180 degrees, space distance of lambda by 2. Pattern is given by, as you know, ET is equal to cos of psi by 2. Psi is beta d cos theta plus alpha. Substituting for psi, beta is 2 pi by lambda. Distance is lambda by 2. Cos of 180 degrees. Sorry, theta is not given. Cos theta plus alpha is pi 180 degrees. Psi is pi cos theta plus pi. I want ET. ET is cos of pi by 2 cos theta plus pi by 2. Theta is 0 degrees. Cos 0 is 1. Cos pi by 2 plus pi by 2. Cos 180 minus 1. But this is in modulus. You get maximum radiation. Theta is 90. Cos 90 is 0. 0 plus pi by 2, pi by 2. Cos 90 is 0. No radiation. Theta is 90, no radiation. Theta is 180. Cos of 180 minus 1 minus pi by 2 plus pi by 2 0. Cos 0 1 maximum radiation. Maximum radiation. Theta is 270. Theta is 270. Theta is minus 90. Theta is 270 or theta is minus 90. No radiation, 0. So option B is the answer. It's donut pattern. Donut pattern. Option B is the answer. An array of 2-point sources fed with current of equal amplitude and having phase difference of alpha is 90 degrees, distance is lambda by 4, results in the pattern of, trying to consider the normalized fill pattern, cos of psi by 2, Psi is beta cos theta plus alpha. Psi is beta 2 pi by lambda. Distance lambda by 4. Cos theta plus alpha pi by 2. Psi is pi by 2 cos theta plus pi by 2. ET normal is cos of psi by 2. It's cos of psi by 2, which is cos of pi by 4 cos theta plus pi by 4. Start calculating. First theta is 0. When theta is 0, cos 0 1, cos pi by 4 plus pi by 4, cos pi by 2, cos 90 is 0. No radiation. 0. 0. No radiation. Sorry. Theta is 90. Cos 90 is 0. Cos pi by 4 1 by root 2 0.707. It's 0.707. Theta is 180. Cos 180 minus 1 minus pi by 4 plus pi by 4 0. Cos 0 1 maximum radiation. Maximum radiation. Theta is 270. Cos of minus 90, cos 90 is 0. 0 plus pi by 4, 1 by root 2. So you get this pattern. Option C is the answer. Array of 2-point sources. Fed with equal amplitude. Phase difference alpha is minus 90 degrees. Spaced at lambda by 4. The normalized pattern is given by cos of psi by 2. Psi is beta d cos theta plus alpha. Beta 2 pi by lambda. Distance lambda by 4. Cos theta plus alpha minus 90 minus pi by 2. This is lambda and lambda get cancelled. Pi by 2 cos theta minus pi by 2. That is psi value. I want psi by 2. ET normal is psi by 2 cos of pi by 4 cos theta minus pi by 4. Theta is 0, theta is 90. Theta is 180, theta is 270. Cos 0, 1. Theta is 0, cos 0, 1. Pi by 4 minus pi by 4, cos 0, 1. Maximum radiation. Theta is 90, cos 90 is 0. Cos of minus pi by 4, cos pi by 4, 1 by root 2, 0.707. Cos 180 minus 1 minus pi by 4 minus pi by 4 minus pi by 2 cos of minus pi by 2 cos pi by 2 0. 0. Cos of 270 cos of minus 90 cos 90 0. 0 minus pi by 4 minus pi by 4 cos of minus pi by 4 cos pi by 4 1 by root 2. So option D is the answer. Option D is the answer. Actually dear, if you know, if you practice this directly, you can write in the exam. It will save a lot of time. An array of 2-point sources fed with current of equal amplitude and same phase alpha is 0. Space distance d is lambda, results in dash pattern. Normalized pattern is cos of psi by 2. Psi is beta d cos theta plus alpha. Psi is beta 2 pi by lambda, distance lambda, cos theta plus alpha is 0. Psi by 2, pi cos theta. Et normal, cos of pi cos theta. Theta is 0, theta is 90, theta is 180, theta is 270. Substituting. Cos 0 is 1. Cos pi 180 minus 1, it is normalized to maximum radiation. Cos 90 is 0, 0.0, cos 0 1 maximum radiation. Cos 180 minus 1, cos of minus 180, cos 180 minus 1 maximum radiation, normalized. Cos 270, cos of minus 90, cos 90, 0. 0 into pi 0, cos 0 1 maximum radiation. It's a flower pattern. Option C is the answer. Results in a flower pattern. Option C is the answer. F and BW for a broadside array. Beamwidth between first nulls is given by 2 by L by lambda radian. F and BW of a broadside array of length L is equal to lambda. L is lambda, they get cancelled out. 2 radian. 1 radian is 57.3 degrees, multiplying 114.6 degrees. As it is a formula based question, it is very important here. Half power beam width of broadside array. Half power beam width is 1 by L by radian. 1 by L by lambda radian. L is lambda. So 1 radian. 57.3 degrees. Option A is the answer. FNBW of broadside array. Array length L is equal to 10 lambda is. Broadside array. FNBW is 2 by L by lambda radian. L is 10 lambda. It is 0.2 radian. Point 2 into 1 radian is 57.3 degrees. It will become 11.46 degrees. What do you get? 11.46 degrees. Half power beam width of broadside array. Array length L is equal to 10 lambda. Half power beam width broadside array is 1 by L by lambda radian. L is 10 lambda. 0.1 radian. It's 5.73 degrees. 5.73 degrees. Option A is the answer. In an n element array, end-fire array case, main lobe firing angle is 0 degrees. Progressive phase shift alpha is dash. Psi is beta d cos theta plus alpha. For maximum radiation, psi is 0. Phase difference is 0, implies beta d cos theta plus alpha is 0. Implies alpha is minus beta d cos theta. Beta is 2 pi by lambda. No need to substitute, sorry. We need not substitute. Given theta is 0 degrees. Substitute theta 0, cos 0 is 1. Alpha value is minus beta d. Theta is 0, alpha is minus beta d. Actually, in theory, I explained in the Mahamarathon series, I explained about this. Theta is 0 degrees, radiation is like this. Main lobe is along theta 0 degrees, implies alpha is minus beta d. Theta is along 180, alpha is beta d, standard. Need not do it again. Theta 0, alpha minus beta d. How to calculate? This is the calculation. In n element array, end-fire array case, alpha given beta d, Theta, just now I told you. Directly you can write the answer. How much it is? Alpha is equal to beta d. Theta is 180 degrees. Option B is the answer. If you do in this way, it will save a lot of time. But how I got this, I'll explain. Listen carefully. Psi is equal to beta d cos theta plus alpha. Maximum radiation psi is 0. Beta d cos theta plus alpha is 0. Alpha is minus beta d cos theta. Alpha is equal to beta d. Beta d is equal to minus beta d cos theta. Cos theta is equal to minus 1. Theta is 180 degrees. In this way, if you do, you will get the answer. But I already told you, theta is 0 degrees. Alpha is minus beta d. Theta is 180. Alpha is beta d. Theta is 0 degrees. Alpha is minus beta d. Theta is 180. Alpha is equal to beta d. So alpha is equal to beta d. Theta is 180. Directly you can write this case. The previous case now you used to see theta is 0, then alpha. How much is alpha? Minus beta d. Directly you can write. But always learn procedure. Don't try to by heart. Always learn the procedure here. Okay. In n element array, broadside case, FNBW formula 2 by L by lambda radian. In degrees, 1 radian is 57.3, 114.6 by L by lambda degrees. Two by L by lambda radian, 114.6 by L by lambda degree. 1 and 3. Option A is the answer. Formula based, very important. Next question. N element array, broadside array case, half power beamwidth formula is 1 by L by lambda radian. One radian is 57.3 degrees, 57.3 by L by lambda degrees. 1 by L by lambda radian, 57.3 by L by lambda degrees. 2 and 4. Option B is the answer. Two and 4. Option B is the answer. Next. In an n element array, undefined array case, undefined array case, FNBW is 2 into under root of 2 by L by lambda radian. In terms of degrees, 114.6 into under root of 2 by L by lambda degrees. 2 into under root of 2 by L by lambda radian. 114.6 into under root of 2 by L by lambda degrees. 1 and 3. Option A is the answer. Option A is the answer. n element array, in an n element array, n-defined array case, half power beamwidth is under root of 2 by L by lambda radian, 57.3 into under root of 2 by L by lambda degree, under root of 2 by L by lambda radian, 57.3 into under root of 2 by L by lambda degree. 2 and 4. Option B is the answer. FNBW of n-defined array with L is equal to lambda is, consider an n-defined array, FNBW is given by 2 into under root of 2 by L by lambda radian. Given L is lambda, it is 2 root 2 radian. It is 2 root 2 radian. Option C is the answer. FNBW of n-defined array, L is 10 lambda, is given by FNBW of n-defined array 2 into under root of 2 by L by lambda radian. L is 10 lambda, 2 into under root of 2 by 10, 2 by root 5, 2 by root 5 radian. Option B is the answer. In n-defined array case, half power beamwidth is under root of 2 by L by lambda radian. L is lambda, it is root 2 radian. Root 2 radian. Option B is the answer. In n-defined array case, L is 10 lambda, half power beamwidth is under root of 2 by L by lambda radian. L is 10 lambda, under root of 2 by 10 radian. 1 by root 5 radian. 1 by root 5 radian. Option B is the answer. Clear? In binomial arrays, we feed radiators with dash amplitude of current. In a binomial array, the uniqueness of binomial array is we feed unequal amplitude of current, and that too amplitude increases as we move to the center of the array. Amplitude increases as we move to the center of the array. By doing this, side lobes can be avoided, proposed by John Stone. Already a theory on this, elaborated discussion on this we have done in Antennas Maha Marathon series. Please go through it. Binomial arrays, we feed the radiators with unequal amplitude of current. Option B is the answer. Binomial array. What is binomial array? Binomial array is broadside array with non-uniform distribution of amplitude. Because in a broadside array, amplitude is equal or uniform. Here, the binomial array is nothing but an extension of broadside array with non-uniform distribution amplitude of current. So it's simply an extension of broadside array. Very important question. If you don't know this concept, it is very difficult to answer. Broadside array. Binomial array is an extension of broadside array. Option A is the answer. Binomial arrays are proposed by, as I told you, most of the students think that binomial arrays are proposed by binomial or Chebyshev, which is wrong. Binomial arrays in 1929 proposed by John Stone, because John Stone has utilized the concept of binomial arrays, or the amplitudes that are fed to the radiators are similar to the coefficients of a binomial series. As a token of gratitude, John Stone has given this name as binomial arrays. His greatness. But most of the people think that binomial arrays is something proposed by binomial, which is wrong. Option C is the answer. The amplitude of current fed to radiators of n is equal to 5 binomial array is amplitudes of current fed to binomial array is decided by binomial series. So do binomial expansion. Sometimes it becomes difficult for us to remove or remember this binomial series. At least you should know Pascal triangle, because the coefficients of binomial series are decided by Pascal triangle also. One element, only one. Two elements, drop this through one on both sides. As I told you, binomial array has unequal amplitude. So anyways, with one element, array is not possible. With two element, one and one equal amplitude, binomial array is not possible even with the two elements. Interview question. This is an interview question. How many elements are required to design a general array? Two elements. How many elements are required to design a binomial array? 3 elements minimum. N is 3. 1 you drop on either side. 1 plus 1, 2. 1, 2, 1. Unequal amplitude. And it is center, it is more. Corners, it is less. N is 4. Drop 1 on either side. 1 plus 2, 3. 3 plus 1, 3. Sorry, 1. 1. Drop on either side. 1 plus 2, 3. 2 plus 1, 3. Drop the 1. Maximum amplitude in the center. N is 5. Drop the 1. 1 plus 3, 4. 3 plus 3, 6. 3 plus 1, 4. And a 1. This is a Pascal triangle. N is 5 elements for binomial array. 1 amp, 4 amp, 6 amp, 4 amp, 1 amp. 1, 4, 6, 4, 1. Got it, everyone? So it is at times it becomes very difficult to remember binomial expansion. So at least you must remember the Pascal triangle so that you can do it quickly. This is a shortcut method for you. Is that clear? Complete binomial expansion is very difficult to remember. A plus b whole power n minus 1, a power n minus 1, n minus 1 into a power n minus 2b, n minus 1 into n minus 2 by 2 factorial, a power n minus 3 b square, so on. Instead of this difficult one, easy to remember here, and you need to do substitutions and all, which will take a lot of time. The shortcut method is to draw the Pascal triangle. Got it here? The maximum spacing in binomial arrays is a design factor here. Every time I ask you a design factor, it is very, very important. The maximum spacing in binomial array is lambda by 2. Option B is the answer. Side lobe can be reduced completely. In which arrays side lobes are completely reduced? Binomial arrays, where all the elements are not equally fed. Center elements are fed more, corner elements are fed less. Option C is the answer. Tapering is the process of reducing what? Tapering is done by binomial arrays, and what do binomial arrays do here? Binomial arrays will reduce side lobes. Therefore, tapering is the process of reducing side lobes. Tapering is the process of reducing side lobes. Option A is the answer. In binomial arrays, what happens? If you take a binomial array, side lobes are removed. Good, very good. As side lobes are removed, we can use them for tracking purpose. But what is the problem? Directivity is decreased. What is directivity? 4 pi by omega A, beam area. Omega is beam area. Therefore, directivity is decreased or beam area is increased. This is what will happen in binomial arrays. In binomial arrays, directivity decreases or beam area increases. This is a disadvantage. Advantage is side lobes are removed. Therefore, it can be used for tracking. So, what is asking here? In binomial arrays, beam area increases, directivity decreases. 1, 4. 1 and 4. Option A is the answer. This is printing mistake here. This is 1 and 3, okay? Any doubts? In radar applications, radar is used for tracking applications. We use which arrays? Of course, we will use binomial arrays because side lobes are reduced. False tracking cases will be reduced. A detailed explanation about the theory of this is explained in the Antennas Mahamarathon series. Please go to the series dear. In Hansen and Woodyard array, what happens to directivity? In Hansen and Woodyard array, directivity increases. It increases by a value of 78.9%. Undoubtedly increases. Option A is the answer. In general arrays, if you want radiation at theta is 0 degrees, alpha is equal to minus beta d is maintained. But in Hansen and Woodyard array, which is also called as endifier array with increased directivity, endifier array with increased directivity, alpha is maintained as minus beta d minus pi by n. Option B is the answer. Minus beta d minus pi by n. Option B is the answer. Folded dipole antenna offers dash input impedance. A folded dipole antenna offers high input impedance. Input impedance of a folded dipole antenna is given by n squared times of Z11. But Z11 is the input impedance of half wave dipole, which is 73 ohm standard. For folded dipole, n is 2. Number of elements are 2. Therefore, Zn is 4 times of 73. That is 292 ohm. Naturally, folded dipole is offering high input impedance. Folded dipole is offering high input impedance. Rest of the questions we'll do in the next class, dear. Rest of them we'll do in the next class. Thank you all for joining. Have a great day.